Okay, so the idea of an inverse function is, remember, if we go back to our original definition of a function, the idea is you've got a function is like a little meat grinder machine, and you put in some inputs and you get out some outputs, right? So whatever input you get in, you can predictably get the same output out the other end. So the idea of an inverse function is, can we find a reverse process that will take our outputs and turn them back into inputs? Right, so if we have some function which takes our x values and maps them to f of x's, can we find some function which does the reverse process? So this is f is this process here. Can we find some function which takes f of x's and turns them back into x's? And we have a name for this function. Oh, it's called the inverse function, but we have a symbol for it, which is f to the -1. Now it's not, and this is really annoying and confusing, but it's not f to the -1 as in 1 over f. It's f to the -1 as in this thing does the opposite thing of f. And that's a little bit confusing and will cause some confusion every once in a while. But just try and bear in mind that this is just one thing, f inverse. It's not f to the power of -1. Okay, so this function, it does the job of reversing the work of your original function. Okay, now if you think about it, that won't always be possible, because if you think about having, let's say we have an original function that looks like this. Let's say that's our original function. Let's plug in an x value. Let's plug in this x value here, and we get this y value here. Well, if we then tried to make a reverse function, one that took that y value and somehow tried to recover the x values, well, then we'd plug in that y value, but that's the same as that point there, and that point there, and that point there. So our reverse function wouldn't know which x value to hit if all it had to work with was that y value. So this process, this inverse function, only works for one-to-one functions. All right, so we're not going to be able to do this process if functions are many to one like this. We're only going to be able to do it for functions which look like something like that, where a unique x value maps to a unique y value uniquely. So it's for this, not for this. Okay, so it's easiest to understand an inverse function with an example. It's really hard. It's kind of a really abstract idea, and then you do an example and you're like, oh yeah, that's pretty straightforward. Okay, so we're just going to do an example. We're going to start with some function f, and I'm going to define it. I'm going to limit its domain. So it's going to be from 0 to 6. Actually, let's make it a little bit more interesting. Let's make that 6 not included. Into the codomain of the real numbers. And f of x is going to be x plus 1 all squared minus 2. Tell me to slow down or speed up as you need, by the way. All right, so I'm just going to sketch that function. Now, the advice I've been giving you that I better follow for myself is that you sketch your function originally in pencil, and then you limit the domain as you need to. So let me do that. It's going to be -1, -2 is going to be our turning point. And it's going to have a y-intercept of x equals 0, 1 squared minus 2 is -1. So 0, -1. It's going to have an x-intercept, which is kind of ugly and has square roots in it, but we'll get to that in a minute. So something like that. Oh, I mean, I say this a lot. jokingly, but this genuinely looks way better on my page. And then we want to limit to only doing it for our particular domain. So we want to actually just start here at that y-intercept and go up to, let's call that point there 6, and I worked it out earlier, it's going to be 647. Okay, and that actually better be an open circle because that point there is not included. Okay, so far so good. Okay, so that's our function there. And notice that even though a parabola is not a one-to-one function generally, this function f is, because only these pink points here are included, and within that domain, this function is one-to-one, which means we are going to be able to do this inverse function idea. So the idea is I want to give you a y value, and I want a function which uniquely spits out the equivalent x value. Okay, so we kind of already know how to do that nominally. We just call it rearranging equations. Right? So if we started with y equals x plus 1 squared minus 2, and I said the y value is 5, go and find me the x value, well then you would know what to do. You'd plug in y equals 5, and then you'd rearrange this for x. So that's exactly what we're going to do, except we're just going to make x the subject of this. So we're just going to rearrange. So we're going to go, so we rearrange for x. I'm just going to move the x to the other side now because it's going to be our subject. Ooh, is it y plus 2? Okay, so we get something like that. But notice this thing on the right doesn't have a unique answer. So if I give you y equals 5, then you're going to get -1 plus root 7, but you're also going to get -1 minus root 7. So at the moment, we're failing in this process of being able to being able to create a function which reverses the process. If I give you a y value, you're not uniquely giving me an x value at the moment. Okay, so what we need to do then is we need to consider which part of this, the plus or the minus, is actually the bit we're after. So what we need to do here then is we need to plug in one of these points, just some point along here, to check which one does the job. And I'm just going to plug the easiest point in, which is this 0, -1. So let's do that. When x is 0, y is -1. Or for our purposes, when y is -1, x is 0. So 0 equals -1 plus or minus the square root of -1 plus 2. So we're going to come up here. 0 equals -1 plus or minus the square root of 1. And so we're looking at that and we're saying, well, is it the plus or is it the minus? It needs to be the plus. Right? It doesn't work, so it must be the plus. Okay, so we're going to go back to our rearrangement here and we're going to say, okay, x is equal to -1 plus the square root of y plus 2. Okay, at this point, we've got exactly the thing we want. Remember, what we're aiming for is a function where we can plug in any value of x, sorry, any value of y that this graph gives us, and it's going to spit out the equivalent x value for us. We call this relationship here the inverse function. But we don't write it like this because we want to write it using the same sort of formalism as our original function. So what I'm going to do is I'm just going to write it out right next to that original function. It might get a little bit squishy here, but so I want to write it as a full-blown function in its own right. So it's going to be f inverse is how we pronounce this, f inverse. I'm not going to worry about the domain and the range at the moment. I'm going to get to that in a moment. But it's going to be f inverse of, now we always use x as our variable here. Now I know that this thing here has a y in it. So now I'm just going to go through, I'm just going to, wherever I see a y, I'm just going to replace it with an x. So I'm still going to make it a function of x, and we'll see why that's useful in a moment. So what I've done is I've just gone through here and I've basically just flipped the x and the y here. So to make this an inverse, a true inverse function, I've just swapped the roles of the x and the y there. And so this becomes our new function, f inverse. All right, I'm going to think about what that domain is in a moment. But first off, but before I do that, I'm going to sketch this graph here. And once again, I'm going to sketch it in pencil because I don't know what the domain is yet. But if I sketch this graph, then what I'm going to get is, well, it's going to start at an x equals -2. Sorry. It's going to start at, oh yeah, -1, 0. It's going to have a turning point, a sideways turning point at x equals -2, -1. So that's going to be down here somewhere, -2, -1. It's going to pass through that point. It's going to pass through some unknown y-intercept, and it's going to have some general shape that looks like that, a sideways parabola. And of course, it would also go around this way, like that, if we were drawing it out in full, if we had the minus part as well as the plus. Okay, but then we're going to think about what the actual purpose of this function is. Remember, it's, you plug in from the, if you think about the original function, it's, the idea is if you plug in a y value, you want to get an x value out. So what is the function that does that? Well, it's one that reverses all these decisions. So you put in 0, -1 into the original function. Well then, with this new function, you put in -1, the y value, and you get out the original x value of 0. And that means if you put in the y value of 47 into this function, what you're going to get out is going to be 6. So this point over here is going to be 47, 6. And our graph in between is going to look like that. Okay. So notice that these two things, these two graphs here, are reflections of one another. And in fact, I'm just going to add one more point to this. I'm going to add x equals 3 here. So let me add in x equals 3. So this is going to be -1 plus √5. So 3, -1 plus √5. The reversal of that point is going to be to here, and it's going to be -1 plus √5, 3. So every point, every x value has been turned into a y value, and every y value has been turned into an x value. Okay. The shape of this graph, you can see, is actually just that it's a reflection of our original graph. All right, it's been reflected along that line, y equals x. Okay, so now we can ask, what are the domain and the range of this new function going to be? But we can see if all of the value, of all of the x values we're going to plug into the inverse are just the y values of the original graph, then the domain of this new graph is going to be the range of the old one. So it's going to be everything from -1 up to 47. Now, codomain doesn't change. That's always real. But the range of F inverse, so what Y values does it hit? Well, that's just going to be the X values of the old function. So everything from 0 to 6. So the range of our inverse function is just going to be the domain of the original function. So the domain of inverse is the range of original function, and vice versa. Okay, sorry, I know that was a lot of information to take in quickly. Does anybody have any questions about that?
Mr. Lynn.
Yes, Bhavesh.
Um, how would you use this in like a real life scenario? Like, what would this be useful for?
So it's mostly used in a situation where like very common, to be honest, but it's so let's say something like let's say we have for some reason the only examples I can ever think of at the moment are coronavirus, so let's get that. Let's suppose we have a model which says there's going to be this many cases after this many days, right? And that might be a very useful thing for hospitals to be planning for. So let's plug in the value June 6th and see what our caseload is expected to be. That's a useful thing to do. Okay. But the government at the moment has the opposite problem. The government has, let's say I want to open the borders when the caseload drops to less than 10 per week, right? So that's the reverse problem. It's not plug in a date and get a caseload. It's I want to plug in a caseload and then I want the answer to be, well, what date will that be possible? Does that make sense as a problem?
Yeah, that kind of makes
Yeah.
sense. Yeah.
So what you want to do is you want to take that exponential graph or whatever it looks like, whatever that function is that relates date to caseload, and you want to reverse it. You want to make a caseload versus date, so that then they can say, well, what's the effect of, okay, what if we don't wait till 10? What if we wait till it's 8? What date's that going to put us at? What if we, actually, let's be a bit more ambitious. Let's only wait until there's 50 per week. What date would that give us? So that we put in a caseload and it spits out a date. That would be the inverse function.
Oh, okay.
Yeah.
Makes sense.
And the other place you use it, frankly, is just in rotations or whatever. So if you're designing something and you've got some X versus Y shape of your graph of your plan, of your model, or whatever it might be, and you just realize, I just need to rotate that thing 90 degrees. The way to do it is with an inverse.
Oh, okay.
And it will flip it 90 degrees. Yeah. So it's a very, very common thing to use, an inverse function. So what we've so I don't want to lose sight of the general process here. Is what we do is we take our relationship y in terms of x, and we make x the variable, right? We make x the subject. Then we say whatever we've got on the right hand side with y in it, that's our new inverse function. Domains and ranges, we just flip them from the original to the new one. Okay, and that's going to give us our new inverse function. The only really tricky question you tend to get asked on these that's worth making clear for you, oh my God, I just got something in my eye, I'm sorry, is you will quite often get asked, where does this function intersect with its own inverse? So this point here, where the two graphs intersect. And in general, let me just do it over here. In general, that's a really hard problem because you have to set this equal to this. So let me just show you what that looks like. -1 plus root x plus 2 equals x plus 1 all squared minus 2. Now, I have no idea how to solve that. Like, no idea. I'd have to square both sides, I suppose, but even if I do that, I'll end up with a square. Oh, God, I don't know. I don't know how to do it. Okay? But this situation can be salvaged. And it's salvaged by realizing something, which is that because if these two are going to be equal to one another, then what else are they going to be equal to? So what we've said is y equals this thing here is intersecting with y equals this thing here, and we're setting them equal to each other. But at that same moment when they're intersecting each other in really complicated hard ways, they're also intersecting that y equals x line. Because that's the only point where two things can be, two reflections of one another can actually be at the same point is right there on the mirror. All right, so another way of saying these two are intersecting with each other is to say they're intersecting with the line y equals x. Which means we don't have to do this horrible thing here. We can actually just take one of them, whichever one's easier to work with, and we can set it equal to y equals x. So just x there. And we can solve this equation, which is much easier to solve than this equation.
Nice.
Okay, so when you're finding an intersection between a function and its own inverse, always use the y equals x line. Don't try and do it like actually raw from the real function. Okay.